Hello students, and welcome to today's lecture where we're going to go ahead and cover some of the basics about rates of reaction. And in this case, we're going to steal from this little site right here that allows us to have fun little molecules that have ice cream and have bumper cars and whatnot. Okay. And this is really kind of a summary of some of the things that we're going to be covering. And essentially, what we're doing is we're trying to see what kind of factors will affect a reaction rate, and to try and see why some reactions are faster and why some are slower. Okay. And the speed of how quick a reaction goes to completion is going to be its rate. Okay. And, here we have a couple of examples where we have an example of some corrosion going on. Again, that's our oxidation reduction reaction. And that's a very slow reaction. We have baking as a secondary reaction. That's a relatively quick reaction. And then we have explosions, and those are reactions where we have oxidation reduction again happening, but that ends up being a very quick reaction. Okay, so we want to try and find out what's the idea behind why this reaction is so slow, whereas this one ends up being so fast. Okay, and essentially, we want to go ahead and look and see what kind of factors are affecting this in particular. Okay. And the main idea with reactions and kinetic molecular theory is that reactions take place when particles collide together with the right amount of energy, or a sufficient amount of energy, to make the reaction take place. And that minimum amount of energy is going to be called our activation, and it's going to be different for each type of reaction. Okay. And there are two things that are going to affect us mainly that we want to go ahead and keep in mind here. The first is that the frequency of collisions between the particles is going to be relatively important, as well as the energy by which they collide. Okay, so rate is going to be determined by how many collisions we have total, and then the energy of those collisions as well. Okay, if the particles do not have enough energy when they collide, they'll just bounce off of each other and nothing will actually happen. Okay. Alright, so anything that increases the number of successful collisions between reactant particles is going to speed up a reaction. So things like increasing temperature, increasing the concentration, increasing pressure of gases, increased surface area for solid reactants, and any sort of use of a catalyst. Okay. Another thing to remember as we go forward is that your speed of reaction is going to end up, or your rate of reaction will gradually decrease as the reaction goes forward. And that should make a relative amount of sense, mainly because as we go forward, we're going to run out of our reactants gradually. Therefore, we're not going to have as many possible collisions to make it go forward quite as fast as it was in the beginning. Okay, so that's going to be something that we're going to want to keep in mind, especially when we talk about concentration and reaction rates, because as our concentration goes down, there's different rates of change for the rate of change, and those are going to be our different types of orders of reaction that we're going to go over here. Okay. And this is an example of a rate of change. So usually when we go ahead and graph these rates of change, what you'll notice is that we'll have the number of molecules, and usually we'll have two graphs. A molecules will typically be our reactant molecules, and what you'll notice is that those are going to gradually decrease, and they decrease quickly in terms of how quickly they decrease initially, and then they sort of taper off at the end. And the same goes for our products. Okay, and you'll notice that for this reaction rate, it's going to always be number of molecules, which usually this will be in terms of moles, over a unit of time. Okay. The main thing that I want you to see here is that this line is not a perfectly straight line, and it does end up curving. And that's going to be important for us later when we go ahead and talk specifically about the different rate laws, because we're going to go ahead and take a look at the graphical representation of a whole bunch of reactions and then be able to say, oh, okay, this is a first, second, or third order reaction based off of that. Okay. So here we have a reaction where we're going to go ahead and observe. This is one that you guys have already seen. This is magnesium and hydrochloric acid. And we can calculate the rate of reaction based off of magnesium and hydrochloric acid. And essentially what we're going to do is, if we were trying to figure this out, we would go ahead and set up our container, and we would put in our mass of magnesium, and then what we would be able to see is that this mass of magnesium would end up going into our flask and then into a syringe, and we can go ahead and measure the amount of hydrogen produced. The only other equipment that we would need in addition to this is that we would need to have a stopwatch. Okay, and what you'll see is that we'll have a general rate of reaction that occurs for a reaction, where you'll have either something that we'll use for amount. In this case, we use liters of hydrogen produced, or centimeters of hydrogen produced, or centimeters cubed, I'm sorry for the mistake, which is something that we can easily convert into moles, and then we have it per a unit of time, all right? And our rate of reaction is always going to be our y value divided by x, okay? Or it's going to always end up being either, well, it's essentially always going to end up being our unit that we're going to be able to convert to moles, or number of particles, divided by seconds, okay? Like most rate laws that we see in nature, it's always, distance traveled per second or something. In this case, it's actually this rate law is the rate of hydrogen produced per second, okay? And this is just a general idea, making sure that you know what kind of units go with what type of rate law, okay? And it's always going to be per second or time. Time is always going to be on the bottom, okay? Okay. The next part that we're going to go ahead and concern ourselves with is temperature, and how is temperature going to affect the rate of particle collisions. And essentially, I want us to get used to looking at this curve right here, and this is called a Boltzmann distribution curve. Okay, and what happens with a Boltzmann distribution curve is this is an example of molecules at a normal standard state, this black line right here. And what you'll notice is that at spot A, this is where the molecules have enough kinetic energy to collide and cause a reaction to happen forward. This red hump here is going to be what happens when we heat up those molecules, okay? And what you'll notice is that a greater proportion of those molecules now have enough kinetic energy in order to go forward with a reaction. So this is a graphical model of a Boltzmann distribution curve that's essentially showing, hey, more molecules have enough energy to make this reaction go forward, okay? Which should make sense that, if energy is one of our rate limiting steps, if we add more energy to a system, we should have an increase in our reaction rate, okay? Okay, and this is essentially going over the exact same thing, that when we increase, the particles are going to have more energy. This moves so that they move faster. And therefore, when they collide, there's going to be a greater chance that they're going to have enough energy to break those bonds and create new bonds. Okay? And this is something that in Florida is not necessarily the biggest issue because we never have any freezing weather here. But up north, they have an issue where certain car batteries will not have enough energy to cause the actual car battery to go ahead and run properly. Okay. It'll help to preserve the lifetime of the actual battery for a longer period of time because there will be less corrosion. However, at the same time, you can have issues with the battery not being able to deliver enough energy on a given point in time, which is why during cold weather, if you have a vehicle that you usually have to sit out for a week or so, you have to make sure that you start it every once in a while, otherwise the battery will go dead pretty quickly. Okay. So this is a reaction here that has sodium thiosulfate and hydrochloric acid. This stuff sinks pretty bad, by the way. And when we make this, it ends up giving us some sulfur dioxide and sulfur. Sulfur is solid and it turns a solution cloudy and it also makes it yellowy. And so this is an example of, us wanting to go ahead and do a reaction and to see how temperature would affect the reaction rate. And what we could theoretically do here is that we could go ahead and heat up both of these solutions and then test one where it's at room temperature, one where the solutions are heated up, and then go ahead and time how long it takes for us to go ahead and see that the solution ends up getting cloudy. And this is just us wanting to try and problem solve. All right, what can we do to test to see this particular effect going on? Okay. And this is something that for our big lab for this section that we're going to go ahead and look really closely at here. Okay. Next, we're going to talk about concentration and pressure. Okay. And here's an example of lower concentration. Here's higher concentration. And this one should be fairly obvious to us. If we have a higher concentration of the reactants, we're going to get more reactions per a given unit of time. Okay. There are more particles that are likely to hit with enough, with the right amount of energy, and then therefore we'll have a higher chance to have a reaction. And the same thing happens with lower pressure and higher pressure. That at lower pressure there's a lot more room, and therefore there's less chances for them to hit and collide, whereas if we have higher pressure, we're going to have a lot more chances of having those collisions go on. Okay. Next is going to be surface area, and this is something that you guys have seen a demonstration of before. In particular, when we took coffee creamer and we lit it on fire in the courtyard. That's an example of how surface area can affect a reaction. In fact, an oxidation reduction reaction, where if you leave sugar out on the counter, it's gonna, you leave it in a big enough pile, it's not gonna react very well. Okay. But if you make it into smaller and smaller pieces to the point that it's super, super fine, what you'll notice is that now you'll be able to cause a quicker reaction. Okay. And that's our main goal with a lot of these, with a lot of reactions, is trying to speed them up. So if you make high surface area, what you'll notice is that you'll have a higher rate of reaction for whichever reaction that you're actually working with here. Okay. And this is just another example that you can go ahead and calculate this out. In this case, we would notice that we have a gas here that's going to be released. So you could probably go ahead and measure the reaction difference if we used finely powdered calcium carbonate versus a large block of calcium carbonate, and then measure how quickly the carbon dioxide is produced from there. Okay. Next is catalysts, and we're going to have a whole nother section on catalysts as well. But catalysts are going to be things that help to lower the activation energy. Okay, so this is an example of the activation energy without a catalyst, and this is the activation energy with a catalyst. Therefore, if you add one, a greater number of your reactants will have enough energy because they'll be at a lower energy here. Okay. To go back to our slide from before that had the Boltzmann distribution curve, instead of heating up a product, what you'll do is you'll actually just move A over this way. Okay, so you'll move A to the left, and that'll end up making it so that you can essentially create your reaction quicker and faster there. Okay, and here are some examples here of some everyday catalysts. If you ever see videos of somebody stealing a muffler from a car, the reason is that they're actually trying to steal the platinum out of the catalytic converter. And the catalytic converter essentially helps to make carbon dioxide, which is less harmful than carbon monoxide. Iron is used as a catalyst for the Haber-Bosch process, which we went over extensively. And then nickel is used in the production of margarine. Also, you really don't want to eat nickel, or for that matter, margarine. Okay, margarine is one of the worst fats that we have out there. Okay, and the idea is that catalysts help industry work a lot more efficiently. In biology, we end up having enzymes as our form of catalyst, and enzymes are just a catalyst that it's a biological catalyst. And just as a reminder that most catalysts and enzymes are not things that we have to necessarily worry about them getting used up at all. All right. So this is just a basic reaction or rates of reaction discussion, and so we should have enough for us. Some words that you want to make sure that you're good and clear with here are activation energy, catalyst, concentration, and in particular how that deals with not activation, but rates of reaction, enzyme, and then rate of reaction. All right. For now, we're going to go ahead and close off, and as always, stay lazy.